This is part 2 of our presentation. This is the spatial and temporal trends at the watershed stressors, and specifically data from the daily erosion project. And this is linking that with the water quality data that was discussed in part 1. So when we're linking water quality to the landscape, typically we're using like land cover maps. And there's lots of data products available for that. There's the National Land Cover Data Set starting in 2001 and then going up into 2016. And then there's new products. There are other products like the Remote Sensing Lab has completed some land cover maps, and the DNR also. So there's lots of different products out there. Big problem with them is the methods have improved over time, so they're different. And then the categories change. So there's not a consistent land cover map available up until recently with the LC map. I've been writing this for a couple of years. This was just recently released a couple months ago. And it basically gives us continuously processed annual land cover maps from 1985 to 2017. And that will be updated as time goes on. But basically it's done in a consistent way. So it can be used for land cover change. And so that's what I did here. I have 1985 and 2015 land cover maps, and basically, fairly simple classification scheme, but for this type of analysis, that's probably good. And so I did a pixel level. So if a pixel changed from one category to another, that was counted, and then I calculated the percentage of the different changes. And overall, some pretty significant changes, especially in the metro area. And then up here in the arrowhead too, with the forest harvesting. So here, if we look at forest harvesting a little closer, that would be tree to grass and shrubland. And then if you're regenerating the forest, it's going to be grass shrub to tree. So it's going to kind of see how it changed. And then with the earlier, with the what's currently there in 2015. So it's a lot of areas that have been harvested, a lot more than in 1985. So there's more forest harvesting is one factor. There's also some areas where we have trees that are being converted to cropland, and like Becker and Park Rapids in the Bemidji area. And then there's other, some other areas where they're actually going from cropland to treeland in the surrounding areas. So there's, some things going back and forth, so that this is gonna take a little bit more work to figure out what's really going on there. Maybe more time steps in there. Then if we looked at developed, lots of developed in the metro area, but then all of a sudden, and also metropolitan areas throughout the state. If you look at barren, that would be the mining pits that are operating. And then cropland, lots of different areas are increasing cropland throughout the state. To trees. So if we're just going to trees, there's quite a few, like the metro area around there, maybe a lot of suburban areas that people like the trees to grow in the neighborhood. I know my house, we moved in, it was all shrubs, and now it's a all forested area. And that could be what's going on in some of these areas. For wet areas, western Minnesota was very wet in this later period, and a lot of the prairie potholes are filling up with water, so there's a lot more water out in that area. And then the abandoned mines are converted to nice pristine lakes, some of the most pristine lakes in the state. And then wetlands also changing. So we can also look at precipitation and temperature data. This is readily available in lots of different sources. And this is just looking at average and then the change. And what we find, I guess there's more rain or more precipitation in the southeastern Minnesota than in northwestern Minnesota. But if we look at the change, one significant thing, big changes up here in northern Minnesota. So a lot drier than the earlier period here for that. If we look at precipitation and temperature, these are August to September. So trying to link it up with the same time period as the water clarity data. So that's a late summer data. So here's temperature, a lot warmer in southern Minnesota than northern Minnesota. And then if we look at the change, getting a lot warmer up in northern Minnesota than the rest of the state. So some significant changes going on and could contribute to some of those changes in chlorophyll in eutrophication in some of the lakes in Minnesota. So that, here we have the trends again from the earlier talk, and you can see how temperature is increasing over this period, and not quite as much variation for the temperature, the orange one here. When you look at the precipitation, seems like there's more variations, wide swings of precipitation over the period. Here we have the periods of when the imagery was collected for our water clarity data. And as you can see, there's a lot of holes in it. So ideally would be able to fill this in, that we have kind of automated methods would be able to fill this in to get a better handle on what's going on with our water quality with these different conditions from year to year, these wide swings from one period to the next. So for linking the water quality data with the landscape stressors, we're using headwater catchments. These are the headwater catchments linked to the water clarity data. And we have, then we linked it with the land cover change, and then the temperature and precipitation data. Now we use random forest. For those not familiar with random forest, it's a powerful state-of-the-art approach for data analysis. It's an ensemble learning method for classification. It operates on constructing multiple decision trees. So it's kind of, for a buzzword, I guess, machine learning. And then basically what it's doing, it's each tree is grown partially on random. So it's a subsample, random subsample of the training data and also of the available features. It allows for a large number of features, and it identifies the important predictors, and that's how I'm using it here. So the ones with the most votes have the bigger bars up here. And so what we find for water clarity is land cover features are very prominent up there, but then also some of the temperature and precipitation values as well. If we look at cropland, so I have the lakes broken up by shallow, medium, and deep lakes. And so as cropland increases as a percentage in the headwater catchment, what we find is that lower water clarity. But if you, same thing with deeper, but there's always going to be a higher water clarity for deeper lakes than there is for shallow. If we look at developed, the pattern is still a little bit of that pattern, but not as pronounced. And that could be due to a lot of the new best management practices in a lot of the developed areas are actually maybe improving the water quality in some of these spots. And then if we look at cropland and developed, you know, similar pattern, decreased water clarity with more intensive land use. And tree cover would be a benefit to water quality. So the more tree cover, the better the water clarity, and that effect levels out around 30 to 50% from that. So if we look at water clarity change over this time period, what the factors attributed to that are, we find a lot of them are the hydrologic and climatic factors. Those are highlighted factors here. And then also there's land use intensification factors highlighted here. So both factors are contributing to changes in water clarity in Minnesota. With those data, we just had cropland. Well, cropland has changed significantly over this period. And so that really should be taken into account too. I do not have this data at the catchment level. And so right now I'm just kind of, you know, looking at it this way is basically we see that corn and soybean has increased significantly over this period at the same time, whereas small grains and other crops are decreasing. And so the corn and soybean are known to be more intensive agricultural practices than the other crops. Big drop off in 2019. That is largely due to the lack of harvesting due to those wild conditions with a lot of big, really wet fall. So a lot of crops did not get harvested. Here's looking at how corn has changed throughout the state. A lot more increase in corn in quite a few areas here, up to 30 to 50%. So yeah, pretty good increases there. With the soybean, same thing. It's very increases in soybean, specifically up in the Red River Basin. And then if we look at small grain change, big decreases in the Red River Valley. And then for other crops, more in southeastern Minnesota and in central Minnesota, big changes, big decreases. And we can also look at animal units at the county level as well. And that is some big increases in central Minnesota and in southern Minnesota. So if we move to the daily erosion project, what we find is that we have, this is basically calculating the sheet and real hill slope soil erosion estimates in a daily time step. And it's stratified to the Huck 12 catchments, subcatchments, and our Huck 12s into subcatchments. And so those are the flow paths, and they like to have at least 100 flow paths. So these are only on croplands. So it's only, and there are only 15 acre or larger crop fields that are included in this data. And then you can also add other things, the crop residue estimates and Landsat 8 and Sentinel-2 data. So basically it's a wet model. It's using the NextRad precipitation data, LiDAR elevation data, the Surgo soils, and then the land use and management from the cropland data layer. So that is actually has to be updated after the fact. So you can't do that in near real time, but you can add that after the data becomes available, typically in the spring time. Okay, so here's the flow paths. They like to have 100, and so that would be the light blue and the blue would be over 100 flow paths. And so as you can see, it's really targeted towards the agricultural watersheds. For this, I really wanted to link it to the specific lake, so I wanted to do it at the headwater catchments. And as you can see, if I look at 100, I have very few headwater catchments to use. So what I did is I used 50 for the Huck 12s and 5 for the headwater catchments. And this is what I have left. And so we have showing average precipitation, runoff, and then delivery. And we can also look at that in graph form. This is average for the whole, all of the Huck 12s. And then we have water quality, and we can that as well. And here's the maximum runoff. And we can also look at that at monthly data. 2019 was maybe not the ideal time step to do this because we had the big, really wet fall. So it's not typical, was definitely not a typical year for the patterns, but gives you an idea of the kind of data that's available. And here it is the monthly maps this is for the delivery. The data of the erosion, and then if we compare it with the water quality, the water quality is going to be a different seasonal trend than the erosion. Typically, it's more light and temperature driven for the algal blooms in the state. So here we have Huck 12 looking at all the data again using random forest. And the runoff is the big factor. And that makes sense because runoff is what's going to end up in the lakes, whereas the delivery of the erosion is going to, may just stop at the end of at the bottom of the flow path. And so it might not actually make it to the lake. And if we look at these are the greater than 5 flow paths at the headwater catchment. And what we have is temperature again is really becoming is a big factor, and I link this with a lot of the other factors as well. But runoff, and you can see how some of these factors actually come in. This is 2015. These are the red ones are the daily erosion project variables, and you can see where they're falling out. Not the most significant factor, but do contribute more so with the shallower water than the deeper lakes. And if we just look at the 50, if we increase it to 50, the numbers go way down. 2715, and then there's no deep lakes. And so, you know, again, temperature, and then some of these variables, and then for the medium lakes, actually a lot of the depth products actually come in being significant there. So definitely some work to do, and maybe expand these to other areas instead of just the agricultural watersheds could be a very useful tool. I'm just going to leave the summary part here. I've kind of run out of time, so I have that for you. You can pause it and read those, and acknowledgements, and specifically the Bowser would be the new one from the previous talk. So with that, I'm going to stop and